Uh, Hello. All right. Okay. So today, it's been a while, I agree. But today will be um some linear stuff. Yeah. So let's get right to it. So we have a test coming up Wednesday, and also a lab to do. So I have most of the calculations already done, so I'm just gonna set it up in Multisim. So let's bring up that. Just go access my data. So lab 4. Okay. So at the moment I have block B and C calculated. So I'm going to go about and actually setting that up on Multisim and seeing if it works as intended. So if we look at the paper, we see that I have my values here for block C and B, so I'm going to go about as to making the NPN here and then hooking it up, see if I get my right values, or around 14 is what people were getting, and then getting the other one in place and seeing what I could do there. So let's open up Multisim and get it over with. Okay, so we begin. So we need to make a PNP and NPN. So move this over here. So we'll begin with block C. First need an 2N, 2N-A. That one, we're gonna need 4 resistors. I'm also gonna get a variable resistor for later, as well as some capacitors and sources, a ground, and a VCC. Okay, so give me 1 second. All right. So let's see what we can do. First begin by taking this transistor and putting 16.3 volts. Of course, the regulator part we'll do after, so assuming everything works as intended. Flip this down here. Copy here, 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 here. There. Connect it like this. Connect that there. Connect that like this. Right here. Ground. 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 Here. Okay. So if we get our function generator, our oscilloscope, and change these values according to mine, which I have my my collector resistor will be 390. Uh, 390, my 1K at R1 is 6.2K. Here is 1K. And this is at 100 ohms. This is at 2.2 microfarad. And so is this. This I measured at around 51 nanofarad, which exists, so I will write 51 nanofarad. I will place this here, place this here, place the negative at ground. This is 64 kilohertz at an amplitude of 1.5 volts. Oh, amplitude at 0.75. Sine wave. Good. This, whatever. And we will need multimeter across base. And across collector emitter and at the base. So let's check our voltages, see if we're correct, and begin. That is not ground. I am retarded. This is ground. What does our oscilloscope say? $10 per division. It is clipping in multisim and not giving me a perfect sine. Plus my voltage is too high, apparently. So I will disconnect this stuff for now and see what my voltages are. 8.9 is high, 2.2 is a little low, as I set this to 2.3 at the base. So I'm going to move this to 5.6. $5.6K and see what my voltage is now. 8 volts flat. 2.4 is too high. Is there anything in between? Let's see. E24 resistor. .6, 6.2. So I'd probably need to add in between. So 5.1 plus, let's say I want 5.8. So 5.1 plus 700 doesn't exist. So 5.6 plus 200, which does exist. So let's do 5.6. Add another resistor. Make this 200 ohms. Let's see what we get. 8.3 at 2.3. This voltage is a little high, but it's closest as I'll get. I mean, I could consider this, but let's just see what we got as values over here. Let's put this back. Put these back here. And we'll start changing this. We'll put this to 33 nanofarad. And view our oscilloscope. It's still clipping, as we can see, and this oscilloscope is really terrible. Let's put like an Agilent one, I guess. $10 nanofarad. At how much? 10 volts per division? It's barely doing anything. $12 volts peak to peak, which we need 18. So, I mean, this gain cap, actually, probably, let me try this. Let's replace component with a variable cap. And change the values of we want, let's say 33 nanofarad. 100%. So at 60% of 33, it begins to skew up here. Could be a possibility that it needs to be replaced with something else. So I'm going to take this out, take the 100 ohm out, put a variable resistor here, and replace this with a normal capacitor at 51 nanofarad, which is basically how much I have. This is 1K, we'll say 1K at 10% of 1K is 100. I would assume so. So at 10%, it should be what I normally should have, right? Now let's vary this. As you can see, it's really not a sine wave at all, and my voltage measured at the base is very high. If that resistance starts to increase, so I need to keep it around 10. In fact, it doesn't even change the amplification at all, as he said in class. So let's remove this for now. Put the 100 ohm capacitor back. So we know that if we vary this capacitor, our signal will look okay. But the issue is, of course, we can't get this. Can't do this because it's going to be different from what my calculated values are. And in practice, doing it on the oscilloscope actually gives me a nice sine wave, but it's not at 18 volt peak to peak. But that's beyond the point. What we want to try to do is just get this basically $15 volts. Plus our voltage at the base is a little high, but I think it increases because of our capacitors. But that's fine. So what we're going to do is take this, is now create our PNP one. A PNP, in this case, is a little different, but I need to measure my beta first. Or my beta is basically my impedance of this circuit. I mean, is it important for, I think, the regulator? I would assume for now I'm not going to do anything. I'm just going to assemble this, which in theory should give me what I want. So let's go about doing that. So let's open up a new design. Basically copy all of this. Change this value to I have to do it backwards because it is a PNP. R2 ends up at the bottom. RE ends up on top. So I need to replace component. Search. Component is PNP. Okay. In that case, this stays normally. This becomes negative. And this value here, as I have written, is, that is RC. Um, 390, so that doesn't change. This resistor becomes 2.7. It's working backwards. I'm confused. I'm going to put 2.7K while this is 3.3. Actually, no. This is 3.3K. Because it's upside down, so 2.7 goes here. 7K 3k ohms, not 2.7 ohms. This resistance is the same. This gain cap becomes 22 nanofarad. No, nanofarad. These are the same. And yeah. Alright, so let's try it. Multimeter 2. That's wrong. That's also wrong. Huh. Yeah, this is wrong. Multisim. Shit. Should this be 390? And this 100? I ultimately forget. Oh. It's better now. Measure 8.6 volts across where I should be measuring 14. Do I just put 16 volts? Well, the 14's right. This isn't right. Jesus Christ. 3.3K. Okay, no. Is it PNP? Yeah. But it has to work backwards. Do I have it in the wrong orientation? I think I might have. Or, actually... Eight volts at across, which is almost perfect, but my base is all wrong. This is too low, that's too low. I had set this to... I had set that to, oops. $14. I mean, are my numbers wrong? Possibility. There is a possibility that they're wrong, but, 16.3 times 1,000 divided by 14 minus 1,000. $16.3 times... Oopsie daisies. Let me just turn that off for a second. 16... 16 3.3 times, what did I say? 1,000. Divided by 14 minus 1,000. 164. Eh? Okay, my numbers are wrong, from what I can tell. Strange. 14 is equal to VCC times R2, which is here, which I set it to 3.3K. Why is that at 3.3K? Am I retarded? That's not right. Why did I write 3.3? Oh, I see. I changed it to 3.3K, meaning these calculations are different. Oh, shit. Okay. 16.3 times 3300 divided by 14, there you go, minus 1,000 gives me 27. Shouldn't be minus 1,000 though. Shouldn't. It's 3.3. Huh, wait a minute. No, this is wrong. This is wrong. If I have a resistive value of let's say my R1 one is unknown, my R2 is the 3.3K, and I'm trying to find R1. So if my VB is equal to 14 volts, my VCC is equal to 16.3. So 14 is equivalent to 16.3 multiplied by 3.3K divided by 3.3K plus R1. This ends up being R1 is equal to 16.3 times 3.3K divided by 14 minus 3.3K. That's hard to see. Is there a way I could bring up the contrast on this? I guess. Whatever. So 16.3. Let's do it here. 16.3 multiplied by 3300 divided by 14 minus 3300 give me 542. So all this is wrong. I need to calculate a higher value. So I need to choose a really high R2 to be able to get the values I want. So let's say we have 10,000. Multiply that by 16.3 and divided by 14 gives me about 1K. Divided, oh, no. Shit. Minus 10K gives me 1.6. If we look at the R values, 1.5, 1.6 exists. 1.6K. So I could use a 1.6K for my R1. So this goes to 1K. 1.6K. And this is at 10K. Let's try it now. That seems about right. This is not. Voltage measured across the emitter capacitor should not be that. Let's switch this. 10K. This with 1.6. Would that change anything? Oh, sort of. 2.2 volts. And 14. In the opposite direction. This is not exactly what I wanted. 1.6K. I wanted the opposite direction. I want 10K down here. I want the voltage at the base to be near 14. But the voltage across here is not. So we'll put this to 390 and this at 100. And it fucks everything up because it's upside down, so it is set up this way. Unless my calculations are wrong again. I mean, continuing further down, we see that we need to deal with finding the current and the emitter voltage, which is 14 plus 0.7. So the total subtracted by that gives us 1.6 divided by 100. Then we do KVL and we get a value of 409 ohms. So I guess I could redo this. Which, if we do 16.3 minus 8.15, which is the voltage, what our voltage across the emitter and collector should be, subtracted by 1.6, which is the difference of the base and the source, divided by my current value, which is 16 milliamp, gives me 409 ohms, which I chose 390. So 390 will be the voltage of the collector, which is here. No. Which is here. Or I guess it's backwards, so yeah, it should be here. But I'm getting 300 millivolts across. for some whatever reason. I'm gonna put this back. I'm gonna put this back and this back. Go for my first design. Take this, put it in here. In this case, this is a point. It's 150 millivolt peak. It's a little nasty, but 500 millivolt peak to peak. That is not amplifying it very much at all. Let's bring up the gain cap. 1.18 volts, a little better. Let's bring it up. Let's look up cap values. Actually, we should keep. I'm gonna bring this up. Cap values. Jesus. Standard capacitor values. There it is. It's the microfarads. I don't give a fuck about microfarads. And nanofarad. There's one. Nanofarad. Okay, so we decided to increase it from 51. Okay, open this. Thank you. 56, 62, 68, 75. So let's put 75. Not 75 farads. One 1.69, 1.7, 6.1 nano. 61. My bad. .39. 63. Jesus Christ. 63 nano. 1.44 volts with a really disgusting looking signal. But it is amplifying it. So let's test it out. But our voltage is completely wrong. Let's just throw it into the mix. Give me 1 sec, I'll be right back. Okay. So yeah, let's take all of this and just slap it in here. Fortunately, okay. So I'm going to place an input there. This should be a 7. We're going to take 2 oscilloscopes and we're going to measure. It should be 0.15, 150 millivolts. Okay. So for some reason, the first oscilloscope is measuring an amplification of a lot, which to me doesn't make any sense. I'm going to remove this. Is this not set to... Oh, this wasn't set to negative. Oh. That explains a lot. Okay. I'll just put this at the bottom. It doesn't really matter. Connect it. Come on. But why is it amplifying it so much? Oh, 1.3 volts. Okay, yeah. Alright. So I have 1.3 volts amplification over here, which is about right. Wait, peak to peak. Yeah, it's about right. 1.3 volts peak to peak. From there, I then need to go here. That looks disgusting. Alright, it's fine. I'll auto scale and all our problems will be fixed. Now here, 11 volts peak to peak, which is low. And clearly it's not nice sine waves at all. But our voltage seem about right. Unless I change the gain. I mean, of course, I have to consider my amplification based off this, because I might be able to measure what the actual resistance is of the entire thing. Can I do it this way? Is this a possibility? R. Nice. Fantastic. It's exactly what I wanted to know. Doesn't really tell me shit, but okay. So our voltages were wrong, but I could alter that by two ways. I could either, one, mess around with a cap here, so I'll replace this with a variable capacitor at 51 nanofarad. Actually, at 102 nanofarad. Place at 50% to be exactly 51. And I could take this variable resistor and place it in series here. Now this is going to mess up my amplification for sure, but I could test it this way. So this is what we're getting. We're getting really nasty stuff. What if it happens if I increase this ever so slightly? By decreasing it here, the gain at the bottom doesn't increase, so I'm going to increase the gain a little slightly. 75%, 100%. Of course, it looks disgusting, so let's vary this. What happens here? Of course, it drops my amplification on this side and doesn't affect this. So I get a lot of clipping this way. I mean, someone's point of view, if you do this, that looks the same. But it is an amplified signal as opposed to this one. So, in theory, is this acceptable? I wouldn't say so, but it sort of is. Whatever the case may be, multisim isn't obviously the determining factor of if this is actually good. So, whatever. I'm going to save it. I'm going to say lab 4 to my network. Cancel. Save it there. Okay. No. So that's pretty much the multisim of that. This is 10K. This becomes a 1.6K, which I changed over here. From the calculations, I just changed those two numbers. Everything else should be fine. So the best way would be now to test it. I do have an oscilloscope. I wouldn't be able to show it on the stream, unfortunately. But I could assemble it and then measure the voltage with a multimeter. So let's first, but before we do that, let's just get our notes ready for the test coming up Wednesday. And then do that quickly, and then we'll, I guess, end the stream at this point. So let's get our things ready. Give me 1 second. So what do we have? So I have my formulas page talking about the diodes at the beginning. Let's go straight to the PNP and NPN. So we first should discuss MPN. So BJT. I'm doing this with pencil as opposed to pen because I don't want to mess up. We'll do NPN first. So what do we want to know? We want to know DC bias. So DC bias, the first step is find R1/R2. I should put or R2. R2 with voltage divider. And then 2 is find RC. First by 1, VCE is equivalent to VCC divided by 2. 2. Let me change a few things. I just want to... a few properties, configure video, so that you can actually see... No. Mess around with this so you can possibly... It'd be too low brightness. Yeah. Anyway, so we have VCE, VCC divided by 2, basically. Then we want to find what is VE. Well, VE in an NPN is VCC minus 0.7 volts for the diode, because it's in series with the diode. That value, VE, divided by RE is equivalent to IE, which is, give or take, IC. From there, you do KVL to do VCC is equivalent to VCE plus VE plus IE, or IC rather, times RC. And then you isolate RC. For PNP, on the other hand, you do 1, find R1 or R2 with voltage divider. I should make a note here. Example, voltage base is equal to VCC times R, it would be R2 divided by R2 plus R1. Is that correct? Am I... Yes. Anyway, but whatever, this R value is of the voltage of the base in parallel with the base, which if we look over here, voltage base and then R2, the voltage here is the same over here. So that's what you want to consider when you're doing voltage divider rule. So I'm going to just draw a quick line that connects both of these together to negate. From there, if we want to find RC, let me just decrease it one more line down. RC is equal to one VCE is equivalent to VCC divided by 2. 2 VE is equivalent to VCC plus 0.7. Therefore, VCC minus, therefore, VRE is equivalent to VCC minus VE relative to ground. This is when you're measuring VE, it's relative to ground, which is equal to VRE divided by RE is equal to IE, which is equivalent to IC. And you do KVL, which is VCC, equals to VCE plus VRE plus IC times RC. So that would be for both. It's the only distinction is what you do with that diode, depending on the PNP or the NPN. But for both, what you need to do when finding amplitude and Zin. So what we need to find is we need to find beta, we need to find C1, C2, we need to also look for amplification and Zin total. So in both cases, we have 1 beta, which is equivalent to IE, IC divided by IB, where IB is equal to IC minus IE. Hold on. How to find transistor base current, blah blah blah. I've used the same freaking website 40 times, which tells you, no, not this one. This one's bad. It is this one. IE minus IC. Let's fix that quickly before we make the mistake. IE minus IC. This is purely to find beta. Next, to find C1, C2 is equivalent to C is equal to 1 over omega. Cool. Next, we want to find what is amplification, which is V out over V in is equal to RO over ZE plus RE prime, where RO is equal to RC, or RC in parallel with RL, if there is an RL. If not, it's just the resistor at the collector, to RE prime, which is equivalent to 25 millivolt, divided by IC. That's what I wrote. IE. Well, I mean, it's basically the same thing, but IE is always a higher current. And then ZE is equivalent to RE in parallel with XCG. Then we have Z in total is equal to Z base in parallel with Vita times RE plus RE prime, where 1 Z base is equal to R1 in parallel with R2. So at the input of the transistor, 2 Vita is equal to, like we said before, IC, the ratio of IC IB, 3 RE is equivalent to RE, whatever, 4 RE prime is equal to 25 millivolt divided by IE. So we have our Vita calculation, also the if we ever need to find the current, if not given, but we're given these other two values. We have our values for the input and output caps. We have our amplification formula, which consists of RO, RE prime, and ZE, as well as Z in total, which is Z base in parallel with Vita, and that's multiplied by RE and RE prime. Other thing we need to take in consideration are two other things, where note 1 that Z in base or Z base must be greater than 10 times R2. I do recall him mentioning something in a previous lab. R2. No. Where does it say 10 R2? Shit. I'm not seeing it. I'm not seeing it. Ah! I do note see, VC, via, okay. Simplicity is equivalent. I don't see it. I'm retarded. It's fine. It's absolutely fine. Basically, Z base has to be 10 times, has to be greater than 10 times R2. Can we say this is true for example block C? My block C, my R2 is 1K. And my R1 and R2 in parallel is 1K and 6.2K. So if we do it on calculator and we do product over sum, so has to be greater than 10 times R2. Oh, my thing doesn't work. Does it not? It doesn't seem to work. Huh. Does he have it written here? Must be less than 10 times Z in. Huh. So my values are wrong. I need a way lower value for... But wait, what the fuck happens then? Let's say I were to use 100 ohms. Wait, that's strange. Hold on. Where R2 is a voltage divider resistor from base to ground. If this requirement gets ignored, the amplifier might not work due to loading effects. So 10 R2. Has to be less than the Z in base. So I need my R1 to be very low. Or very... Hold on. How can my R2... That doesn't seem right at all. That just seems really strange. Has to be less... Z in base must be greater than 10 times R2. How can that be possible if Z in base is... Oh. I'm looking at the wrong thing. This is Z base. Oops. Ignore what I said. Z in Z base. Z base, also known as Z base. Z in is equivalent to R1 in parallel with R2. Okay. So my z base, RE plus RE prime times our beta, 208. My RO, RE prime of 1.625, 0.5625 plus RE at 100 should be, in theory, less than 10K. Greater than 10K. So 100 plus 1.5625 multiplied by 208 will give me 21K, which is fine. For block B, I have no idea because I haven't measured. So we need to measure this. But basically, this rule states that the Z base, which is beta times RE plus RE prime must be greater than 10 times R2. So now we need to assemble it onto our circuit. Here, on the left side, so if I were to remove this, minus this IC is irrelevant. Here is a 22 nanofarad, which is what I got in my calculation. From what I got, everything else is fine except the first resistor value. So what we need is a 10K, a 1.6K. We have a 22 nanofarad. I need another 2.2 microfarad and a 16 volt source, a 100 ohm resistor, 390 ohm resistor, and then we'll be able to measure the current. So I'm going to take it from here. So we got two 22 nanofarads. And we have our gain cap. So we're going to put these aside for now and work specifically on getting our voltage values right. So what we need is in our case, a 2907. I have a 2907A, which is a PNP. I don't know what else. I would assume that's what we need to use. Or any PNP transistor. So the little tab is right here. So let's go about making it. So we have a 300 ohm resistor. We have our 100 ohm. We said we need a 10K. Oops. 10K, 1.6K, and that's it. And RL becomes the Z in of block C. And our beta. To find our beta. But we just need to assemble it first. So we need our 4 resistors. So we need our 10K and 1.6K. So let's find that. My first block of resistors, I need a 10K. I don't even think I have a 1.6. I do not. 10K, there's a pretty good chance I do have. Brown, red, orange? No. Brown, black, orange. To prove, set this to resistance. $9.4K. So this is right. Now I need a 1.6. Do I even have something close to a 1.6? I have a 15 ohm. I'll be damned. No, wait, no, this is... No, that's 100K. No, that's 1 mega. I need brown blue. I might know where. Closest thing would probably be at 2.2K. So let's look for a 2.2K, which should be triple red. I'll use this beefy one here. It's probably a half watt. Once again, let's prove it. Be it that it's hard to see on stream because my webcam is not very good. That says 2.2K. No autofocus. It's fine. So let's assemble it as we need to. In this case, the 2.2, hence the photo, will go R1, so it will be near the base. So one at the base. Okay. The base is up here. Then we need a R2, which is a 10K, which is this one right here. And then we need a collector resistor at 390 ohms. Like so. So what I've done is bridged here and here so that they're both going to get 16 volts. Put one here. I will then connect the grounds together. I'd assume I'll just put a wire here. Connect it to ground this way. And then have my ground lead over here. So Voltage source set to 16.3 volts. Ground on ground. Positive on positive. And let's go. So if we begin by measuring the voltage here. Oh, oops. We get 0. Hooray. $16.3 volts. Nice. So now what we're going to do is measure the voltage across the emitter and collector. 7.4 is a little low, but it's all right. Now I'm going to measure on the base and ground. 13.5. So my values are a little skewed, be it probably because of that 2.2K resistor over here. So I could look for something equivalent, a 1K and a 560K, 60 ohm rather. So let's go about and find one. So 1K resistor, like so, with a 560 ohm. This I'm going to have to go through here to find it from last semester. $560. So we got my 560. We will put this in series with my 1K, and we will place it at 16.3 volts, like so. Let's once again take our leads, turn on our power, and measure once more. Between both points, 16 volts. Between emitter collector, 9 volts, a little high. 14 volts. 14.9. Fortunately, 9.5 is 1 volt too high. This over here gives me almost exactly 14. Be it, I might have to increase it slightly. So the closest one value after that, after 500, is 62. 620 ohms. Our value we calculated 1.6. So that would be almost perfect. Remove this resistor and go find another one. This at 600 ohm I might not have in the kit we got first semester. There's a possibility I might have to go in my own. Yep. Oh, well, it's all mixed up, but whatever. Just put this away. 680. Closest one I could find was 680. To prove that it is 680, that does say 0.680 kilo ohms. Let's change it to 600 ohms. Right. Place this in series. Right over here. Actually, give it a little bit of distance. Like that. Okay. That does the DC voltage. So if we measure the resistance across here and here, overload? Question mark? Probably have to do with that power supply. Regardless, let's just measure the voltage. Once again, let's measure at each point. Click, confirm it's at 16, and let's measure across there. So we get 8.7 volts at the collector emitter, and from the base, almost exactly 14. So this is, I think, by maybe lowering this to 1.6, which it is possible, I just don't have the resistor, I'd probably be able to get it spot on. Now, what's important is to see if it amplifies. I unfortunately can't really show you, but I could set it up so that I can. So we need to take this capacitor, this gain capacitor, and put it in series, parallel, my bad, with RE. And connect it to ground. Then these two capacitors here, one for output at the collector, I'm going to move this position of a few things. The leads on this are very, very thin. I don't know why that is. Why are they so thin? Why are you so thin? And input signal. Input signal here, and an output would be nice. So this is basically my circuit. Can't really show, unfortunately. Don't have a oscilloscope cam. But basically, this stream we looked at how I got about to get this, a few mistakes I made that I did fix. One thing I do need to measure. I almost completely forgot. something that I just remembered. This is irrelevant. Is my currents. Current going into the base and current at the collector. So for this, we will use these to help us out, as well as our multimeter set to current. So this can measure in amps, and I don't know if the range 10 amps, 6 amps, 6 or 10 amps. Probably I'll be able to see it. So we want to measure first the current going into the base. I'll put this on my black lead like that, and this on my red lead. So first, what we want to do is take the base out and connect my positive lead to the parallel resistors at the base, and then my negative lead to the base. And then start. First things first, I should power my stuff. Makes sense that I do. My multimeter does not measure much, fortunately. Probably because it's not made for that. So I'm going to bring right back and get another multimeter. I'll be right back. So this multimeter unfortunately can't measure low currents, but this one can. So I'm going to remove the leads it came with, place one at common and one at 300 milliamp. Place it to amps. and turn it on. So, right, we have the negative current value because it's a PNP, but we have a current of 0.07, which is 70 micro. 0.07, 70 microamps, which I think makes sense to me. So 70 microamps, give or take. Let's take our leads off. Oh, oops. Not off the circuit. Take our transistor. Place it back in the place it needs to go. Like so. Now we want to find the collector current. So just take this. And place it at the collector. Power. So we measure 13.93 milliamp. So if we take our value of 14 milliamp and divided by 0.70, so we have 70 to the negative 6. We get a value of 200 beta. So our beta for block B is give or take 200. So I'm going to write that down. IB is equivalent 70 microamps and IC is equivalent to 14 milliamp, where beta is equal is maybe 200. So from there, we are able to get our value. Oh God, everything's falling. So let's disconnect power. We do not need these anymore. Let's put these back. Okay, let me just disconnect everything from my multimeter. Clean up the stuff. Move this out of the way. So, what we have determined this doesn't matter. What we have determined that for block B, if our beta is 200, then we could find and prove if R2 at 10K is good enough. So our formula for Z base, so Z base is equal to, try and write this in pen. z base is equal to beta times 100 RE plus RE prime. In our case, RE is 100 plus 25 millivolt divided by 16 milliamp, which is 101.5625 multiplied by 200 on a calculator. 200 times 101.5625, 20,000. 20,312.5. Problem with this is that R2 is greater than. So I need to lower my R2 so that this is well enough. So I need to lower it. It needs to be, from what we said, that Z base must be greater than 10 times R2. And my R2 is at 10,000. So I need to lower this value so that, and still keep the same, but lower that value so that this factor is true. We could say that if 14 is equal to, because if my thing is 200, so we need to keep our value under 20K. So 10 times 5 won't, 10 times 1K, we do 1K multiplied by 16.3 divided by 1K. 1K, actually, let's do it 1.5. So 14 is equal to 1.5K times 16.3 divided by 1.5K plus R1. R1 is equal to 1.5K times 16.3 divided by 14 minus 1.5K. R1 is equal to, so 1500 times 16.3 divided by 14. We're looking at 246 ohms in its place. We can try to increase this a little more. I mean, the closest $240, we have a 240 here that exists, as well as 270. Let's say we calculate at if is equal to 1.8K. So we get 18,000 as our comparison here for Z base. So 1.8K times 16.3 divided by 1.8K plus R1 do it all on my calculator. 16.3 times 1800 divided by 20. Nope. 16.3 times 1800 divided by 14 minus 1800. 295. 71. If we look online, 295, the closest one is 300 ohms. So basically we have this or this. Choice between either 300 ohms or 240 ohms. And we will be within our value here. We respect this factor. Unless I keep it the same and nothing happens, but I will apply this if it doesn't work. So, well, interesting, very interesting. Let's mark that down. That ask for 300 ohm and 240 ohm resistor and 1.6k ohm resistor. This is for the R1. Oh, no. No. We just calculated that this doesn't work. So I'll write no question mark. Okay, well, interesting stuff. I'm gonna get off now. Hope this was somewhat helpful, but I guess tomorrow I could stream as well. We're gonna have a wireless, so I might work on that, study more on linear, and plus my other classes, of course. But pretty much that's it. I have done my integrated lab report. That's done. Wireless also done. So that's it for now. Nothing networking. We might have something, then I'll show if we have a lab or another packet tracer. So yeah. All right. Till next time, guys. Till next time.